Okay. I think you can start now.
Hey everybody, I'm Alina, welcoming you all to the live session of Astronomy on Tap Koeln. Apart from the committee members, we have two guests today. So as you all know, we have been posting Astro Quiz sessions every Monday. Last month, we decided to announce who all are answering our questions correctly. Also, we decided to choose one person from them to be on the live session with us. So here we have Ekaterina, a PhD student from University of Cologne as this month's winner. Congratulations. So would you like to say something about you, Ekaterina?
I can just make a short comment. Hi, everyone. Yeah. I'm Katya. I think it's a bit easier. And yeah, I'm just a PhD student at the University of Cologne. I'm also doing interstellar medium, but I'm doing more supernova and supernova remnants and emission from them. And today I have a guest with me, my husband. So you can also introduce yourself.
Hi everyone, I'm Alexander. I'm also an astrophysicist, a PhD student, but at Bonn, Max Planck Institute for Radio Astronomy, I'm working on pulse astronomy in a group of Michael Kramer, but I'm not so familiar with ISM, but it's also interesting to listen to. Thank you.
Yeah, we will translate an opinion like a person who knows about interstellar media and who haven't seen it.
Thank you both. We welcome you. And our guest, like our audience will remember Professor Michael Kramer because we had already a session with him and he was talking about pulsars. And so thank you so much for all your comments and responses from the audience. And we are thrilled to see you all. I hope you already watched an introduction about today's speaker. We have Stefano with us. Stefano, thank you so much for coming.
Thank you.
He's a second year PhD student at University of Cologne. He did his previous studies in Italy and moved to Cologne in 2019. He's working on star formation and he'll be talking about how simulations are used to understand star formation in molecular clouds. Before we start our session, I have like some things to tell you. You can leave your comments or questions in the live chat session in your YouTube. If you're watching later this video, then please feel free to contact us via email or Facebook or Instagram from AoT Koeln. Also, after the talk, we would be we are having an exciting astronomy news session from the last month. So grab a beer, lean back and enjoy. So you can start whenever you are ready, Stefano.
Yeah, okay. So yeah, thank you, Elina, for introducing me. So now I will try to share my screen. Hopefully it works smoothly.
Yes.
Okay, you should see it in full screen now.
Yes, yes.
Okay,
you're
perfect.
Good to go.
Okay. So yeah, hi everyone. I am Stefano Ebagezio, and yeah, so I'm PhD student in Cologne, and today we'll discuss about the role of molecular clouds in the formations of stars. So we will see a bit where stars form, in which environments they form, and how can we observe or know facts about these environments. So the first thing interesting to say about that is that at today's time, we do care about the environment where stars form. But this question could never have been asked before 1 centuries or a bit slightly more. As of now, because in the past, what people thought about the structure of the universe was something completely different, and so this question, so how stars forms, could not have made any kind of sense, because in the classical age, what happened is that people used to think that the universe is organized somehow in different circles, different spheres, which have, of course, the heart in the center. That was what they believed, and then a series of different spheres, and one of those spheres contained actually the stars. This theory, this model, was firstly developed in the ancient Greece. For example, a good description of that is contained in Aristotle's On the Heavens treaty, which describes this kind of model. But what's still the standard theory, even way later on, for example, even in the beginning of 14th century, the Italian poetry Dante Alighieri, in his comedy, again made use of a model of universe more or less exactly like this one. So in these models, the two key points were that were that the stars are eternal, so they don't have any sort of life cycle, so they don't form, neither they live nor they born, nor they dead, and also they are fixed because they are placed on this fixed sphere, and so they don't have any kind of relative motion among each other. Now we know, of course, that this model is not correct, and but also those people at a certain point started having a sort of signals of alarm. So they started knowing that something could not be correct in this model. Why? Because in several times, but in particular in two different episodes during the Middle Ages in 1006 and 1054, they saw two strange stars, so two new stars which used to be in the sky before, and which they disappeared in a few months. And they had, of course, no idea how to explain them. It was completely impossible according to their vision of the universe. They realized that something was wrong. Here is an extract from a Middle Age report, which say more or less that at that time, so in 1054, a very bright star appeared in the sky the 13th days of that month, at the beginning of the night, close to the crescent moon at that time. So they saw a very bright star, Stella Clarissima, in the sky, and they couldn't have an answer for that. Now we know what those stars are. They were supernova that at that time exploded. And still today we can see not that those stars anymore, but they are remnants. The 1006 star now is so the remnant of that explosion. It's now visible in ultraviolet, and it is this image here on the left hand side. And the star exploded in 1054. It's the very well known Crab Nebula at today's time, which I'm sure you already have seen many times, and is this nebula here on the right hand side here. So yeah, now we know that stars have a sort of life cycle. They form, they live for a while, and then they die. And we know that basically from the moment when astronomers start to observe at the characteristics of the stars a bit more systematically. And here there is basically what they used to do. So here you see a diagram where you have the temperature of the star on the x-axis and their luminosities on the y-axis. And you see that stars are not distributed uniformly on this diagram, but the great majority of the stars follow a sort of line, kinda straight here, which are the so-called main sequence stars. And then when these stars grow older, they put themselves in other parts of this diagram according to their magnitude, their temperature, and whatever. So studying these kind of diagrams, astronomers realized that so stars have a sort of life cycle. But actually, the point where we are mostly interested tonight is not this life cycle itself, but we would like to know a bit more about what happens before. So what happened before stars form? And in particular, we are interested in answering to two questions. So first of all, in which environments do stars form? And second, how astronomers are able to observe this environment where stars form. So now, in order to proceed, we have now here to be slightly more technical, but it's needed because we need to have clear in our mind at least some very simple physical principle that enables us to understand what's going on when stars form. So let's consider a sphere, a blob of gas like this one, which you can see here in this very, very simple scheme on the right-hand side of the slide. So a blob of gas, which a certain maybe density gradient. So this blob is more dense in the center and less dense in the outer part. So if we have a sphere of gas like this, what happens is that there are two main forces which act on this blob. First is the gravitational force, to which we are all familiar with. It's nothing else than the force that every day keep us attached to the Earth's surface. So here also we have a certain amount of gas which does have a mass, and so it's very reasonable to assume that we have a gravitational force that tends to collapse the structure, because the outer part of the sphere is attracted by the innermost one, and so this sphere tends to collapse. But it is a gas, so on the other hand, we also have the pressure of this gas, which has the opposite evolving and so on. And what does it happen to a cloud when stars form in a certain position? We can already see. We have this very violent phenomenon, we can say, in which the cloud itself is dispersed. Why does it happen? It happens basically, maybe you can go a bit backwards. It happens because once the star is formed, the stars exert a sort of feedback on the cloud, so stellar wind or whatever. So these stars emit radiation, particle, and whatever, and so it's like they originate a sort of wind, a real wind that tends to disperse the cloud, and you can see here. So the cloud loses part of material because it goes outside due to these stellar winds that we have once stars are formed. So this is an example. This is a very simple one because the cloud is spherical, but of course we have something more complex. So here is another example of our simulations. Here you don't see stellar feedback because this is a simulation where we artificially suppressed it. But you can see that time by time more and more dense structure are formed. We didn't see anything with so just very unrefined structure in the beginning, and now we have way more refined filaments, sheets, or whatever. So again, we can simulate this evolution of cloud. So what did we learn so far? We learn that, first of all, that the clouds collapse because of the Jeans instability. Then we learned that the stars form in the densest part of the cloud, like in the movie you saw two slides before this one, and then that stellar feedback may disperse these clouds. So I guess you already have an idea now of why numerical simulations are useful in this field. So first of all, they enable to follow the evolution of a cloud for several million years. So I didn't say it explicitly so far, but the typical life cycle of a cloud lasts several million years, in most cases also several tenths of million years. So it would be completely impossible to observe a single cloud evolving in a human lifetime. So that's already an important reason. Second one is that analytical calculations are, of course, not doable with this detail. So you can analytical derive and do calculation on simple principles like the gene's instability, or of course even something a bit more complex, but you will not be able to model in detail, for example, an outflow of material like you saw again in the movie. So you can get the basic principles, but you could not be able to draw a picture as detailed as we do with numerical simulation. So that's a second important reason why we use them. But there is another one, which will be the second part of this talk, which is that numerical simulations help in addressing observations. So in a certain sense, they help to tell the observers what they have to observe in the sky. That's a very generic statement, but now we are going to see an example of what I mean with help in addressing observations. So again, before we go on, just another very small theoretical explanation. I'm sure you already know that hydrogen can be in general found in three different forms. So it can be ionized. That means we have just the nucleus, so a proton and nothing else. It can be molecular. So we have the proton plus an electron orbiting around the nucleus, or we can have a molecular form. So basically the hydrogen molecule in which two atoms joined together. So what is, in your opinion, the most important of these three forms that we need when we study a molecular cloud? Well, the name itself suggests that we have to be particularly interested in this form, so the molecular form. Not that the other two are not so important, but on the densest part of the cloud, we had said we had the molecular gas. So this one will be the most relevant in those regions. And indeed, that's true. For example, there is a lot of literature which confirms that okay, H2 is the most common forms of hydrogen in the star forming regions, and indeed it is strictly related with star formation itself. The most molecular hydrogen we have, the more intense star formation we also have. Here you see in this in this figure taken from Bigel et al. 28, there is the density of molecular hydrogen on the x-axis and the star formation rate. So basically, how many stars we form in this particular cloud on the y-axis, and you see that there is a correspondence. So the more molecular hydrogen we have, the more stars we form. So it is indeed important to look at this. But unfortunately, there is a problem with that. H2 does not emit light in such environments. So in principle, H2 can emit some faint light, but not in this density and temperature regimes that we have in the densest part of the cloud. So it's dark. We cannot observe it directly. If we want to see indirectly where H2 is, we have to use some alternative tracers. How can we do that? Let's see again. Here we have another example of a simulation of our group. Here you see again a cloud, and in particular you can see the totality of the cloud, so all the gas together. Here you see what we are in this particular case interested in most, which is H2, so molecular hydrogen. And here you see other two species with our CO, so carbon monoxide, and C+, which is the ionized carbon, so carbon which lost one electron. These are not observations, so these are actually how the cloud is, because we did simulate this cloud. So simulated means knowing at each position what is inside, so we know how the cloud looks like. And so this is just a picture of how this cloud is. Remember that we are interested in looking at H2. In reality, this cannot observe. So what can we do? We could, for instance, considering other two species like CO and C+, which do emit light. Indeed, if an observer would look at the CO and C+ emission, this observer would see something like this. So these two other images on the bottom right of the slides are what we call synthetic observation. So what an observer would see if he looks at these clouds. And you can see, so these two elements are visible, and these hypothetical observers is interested in understanding how the H2 would look like. And so now you understand why numerical simulations are needed, because an observers can observe these two things, but we need simulation to go from this to this. For example, we can see that, for example, CO is very bright, so it emits a lot of light in some regions here and here as well, that we know from our simulation truth that they correspond to the most dense regions of the cloud, so the regions where we have the most of H2. So these simulations enable us to say, okay, if you want to look at the densest region of the cloud, you have to look at CO. But let's consider, for example, this triangle here. This triangle does have some H2, but it's practically invisible in CO. We have something, but not much. Conversely, there is much more of this here in C+. So C+ is useful to look at less dense regions of the cloud. So combinations of that enable to reconstruct indirectly what we are interested in. And that we can do because we know the simulation truth, so via our simulations. So that's what I said before, that simulations tell the observers what to observe if, like in this case, he wants to look at something not directly observable. So now we are already almost in the end, but before we finish, I think there is another point which can be really interesting also, because it enables to show the power of this numerical simulation, and this one. So if you remember, the very first image of this slide, so the very first slide contained the pillars of creations, but so far we didn't talk about any kind of pillars. So now let's try to analyze this pillar a bit more. Do you manage to recognize in this image here the pillars of creation again? This is a different image respect to the previous one. Yeah, if you look a bit, you can see that here we have our pillars of creation. Here they look different because okay, the angulation is different. Also here we have not only the pillars but the entire cloud. This is the Eagle Nebula. So now the question is, what are these pillars of creations, and do we are we able to model the pillar of creations by using our simulations? So before doing that, let's consider a bit more how the physical situation here is in this cloud. So here we have the pillar, and we know that we have stars which formed in the surroundings. Mainly here, for example, here there is a region where stars formed. So the stars formed here, and if you remember the movie which I showed you before, when we have a star forming regions, we also have a stellar wind which tend to disperse the cloud. And indeed, you see that here there is basically nothing, and just here we have some darker parts or some gas which is left over. Now let's think about what could happen if some clump of very dense gas is located somewhere in the cloud. We can have an intuitive idea of this. So let's think about you are outside in a very windy day. So you are walking in the street and of course you feel the wind in front of you. But now if you go behind, for example, I don't know, if you go behind a very large tree, in that point you don't feel the wind so much because the tree is protecting you from the wind, right? And so here is the same. So here we have some very dense clump of material which is acting like a tree. So these clumps protect the material which is behind them from the stellar wind. And so we form the pillars. So the pillars are basically just column of gas which are not dispersed by stellar wind because of the fact that there is some very dense clump of gas which protect them. So that's the reality, what we observe in the sky. Can we model somehow that? Let's see. Here we have again one of our simulation where we enable star formations. So this is again a synthetic observation of one of these clouds. This in particular is a C+ observation, so an ionized carbon synthetic maps. And in this particular cloud, we have stars forming in these three regions. So again, stars form here, the wind disperses the cloud around this area, but we also have pillars here, like the pillar of creations, because here you see there is some very dense part which is protecting the part behind them. So we can actually reproduce even the pillars by using our simulations. Then, of course, I mean, we cannot aim to reproduce the beauty of the real pillars of creations, for instance, by our simulation. That will be unrealistic. But still, the basic physics, at least, we can reproduce. Here you can really see stars are here on the right, dense clumps of stuff, and then pillars behind. Not insanely different from how we can actually see in the real pillars. So this brings basically us already to the conclusion of this talk. And so basically, what can we take home from that? So first of all, we are happy because simulations reproduce the observer feature, which is nice, because otherwise that would mean that our simulation don't work. Then we saw that the simulation help in understanding complex physics. For example, we saw they help in telling the observers what they have to observe if they look, for instance, at H2. Also, they help us in studying different processes separately, because in our simulations, you saw two different movies before. One of them had the star formation included, and in the other one, we excluded that. So we can, in the simulation, we can switch on and off different processes and see the effects of different processes separately. That's a thing that we cannot do in the reality, of course. But it's also important to point out that real observations and simulations always have to go together, because only comparing our simulations to the real observation can tell us if we are doing correctly, so if the observations are correct, and if they are correct, they can help observers. So there always has to be a really strong interdependence and correlation between the simulation work and the real observation work, because if we join these two parts together, we can really improve a lot our understanding of the universe and of complex physical processes that would be really difficult to understand only with one of these two aspects of astronomy. So yeah, that's basically what I wanted to tell you this evening. And now, if you have any kind of question, I'm hopefully ready to answer them.
That was a very nice talk, Stefano. Thank you so much.
Welcome.
Yeah, YouTube live will be in like some time difference will be there, so we can wait for the questions. So if anyone have a question, we can you can ask now. Okay. Yes. Great.
Yeah, I think I might have a question. You were talking about how you observe, or how astronomers observe molecular hydrogen with these tracer particles. I was just wondering, because you were showing carbon monoxide, which is used to trace.
For instance.
Yeah. And yeah, I think it's very nice that you can get the synthetic observation, what you would expect to see in carbon monoxide from your simulations. But my question is, what are the other types of tracers that you might be able to use, and what is the benefit of using a different type of tracer?
Yeah. So yeah, so in principle, the tracers can be a lot, because in our molecular clouds, we have a really huge variety of molecules. We have most likely several hundreds of them. So every molecule which, or not necessarily molecule, whatever element, atom, ion, whatever, which emits light, which is capable of emitting light, can be used as tracers. So a tracer is basically whatever that we can directly observe. Then, of course, which tracer is the best to trace which part of the cloud, then is object of study. For example, here you already see the difference between CO and C+, so more dense and less dense part of the cloud. But there are many others. For example, in between CO and C+, there is also neutral carbon. Then, especially in recent years, has been used quite a lot, and we also, to be honest, started modeling that, but we had still some issues with our way of modeling. But anyway, so neutral carbon is another tracer which is commonly used, and traces at best the densities in between, so in between CO and C+, so not such extreme dense regions, but also not the most diffuse part like C+. Then there are other stuff. For example, also in this recent years, hydrides, so H something, HS, HCN, and whatever, they have also been used quite extensively to study the very, very dense cores of the cloud. You can already see here, for example, that also CO somehow, here, if you look at H2, you have, for example, here two structures that we know they are separate from here, but here we can really not distinguish much. So for the extreme dense part, the hydrides are also very, very used. And also molecules with nitrogen inside, there are also supposed to be dense tracers. So yeah, you have a huge variety, and depends on which region do you want to observe.
Yeah, Kate, you have a question, right? Yes, please go ahead.
Thank you, Stefano, for a nice talk. I have a bit of general questions concerning traces. There is a well-known 21 centimeter radial line for H, for hydrogen, and I want to ask how it's useful for your purposes. I know it's not H2, but anyway.
Yeah. So yeah, so the 21 hydrogen centimeter, so it traces indeed the neutral hydrogen. So well, it is so in principle it is used. The fact is that for example, so for this, so let's imagine we wanted to use it for a cloud. Okay, we don't expect that it will trace the most dense part, and that's expected because it's neutral. It's atomic hydrogen, so we don't expect to find it here. But what it makes things a bit difficult with the 21 centimeter is that basically, okay, first of all, this emission is normally quite faint. So yeah, so there are brightness problems. Secondly, also neutral hydrogen is kind of diffused everywhere. So neutral hydrogen is very much diffused in the interstellar medium, basically whatever. So when you look at the 21 centimeter line, you always have a lot of background coming from places which you are not interested in, and so also from you and the cloud you want to observe, for instance, and that can create problems. Whereas if you look at more at heavier molecules, like for example CO, like here, or the other one, they are normally not in the interstellar medium, which is not a real cloud. So that's why they are considered like easier to be used for clouds instead of the 21 centimeter line.
Thank you, Stefano, for your answer. And now concerning more relevant for H2, yeah, we all know about isotopes of H, for example, deuterium, and are there any benefits from this difference? For example, molecules of HD or D2, maybe they have different properties in terms of emissivity. That's the question.
Well, in principle, so in general, different isotopes of whatever kind of species, they emit light at slightly different wavelengths. So this is true also for CO, for example. This is 12 CO and 13 CO, which are the two common isotopes. They have slightly different emission lines. According to several isotopes of H2, to look at here, honestly, I don't think they change the situation dramatically, because actually, indeed, the regime where H2 can emit is really far away from the typical condition of a cloud. So I guess different isotopes would not change the situation dramatically. So I don't expect direct detection of them would be much easier. We could, in principle, if we had a chemical network in our simulation sophisticated enough, we could, in principle, model also different isotopes of hydrogen. That would be something we could, in principle, do. So in terms of modeling, provided a complicated enough network, which is not an easy task, we could modeling. But in terms of emission, I don't think it helps a lot in this molecular clouds context.
Thank you. I have a question, like a remark. thinking the H2, it's very symmetric. It's totally symmetric molecule, and HD, it's a bit asymmetric, and maybe it has different properties. I mean, like vibration. I don't know.
Yeah,
you can trace it in other wavelengths, and without the necessity for the purposes of emission. I mean, for emission of H2. I mean, in different regions. Yeah.
Well, yeah. So the fact that it is asymmetric, it definitely helps because indeed the major problem with H2 is indeed the fact that it is asymmetric. So that will help in principle. As I said, I don't think things change in a dramatic sense. So there might be some faint emission that is reasonably expectable. Honestly, I don't know whether it would be at a reasonable wavelength to be used actually. So, and how bright these emissions will be. So I don't know which wavelengths do we expect to have and how bright they will be. So yeah, I mean, in principle, that's possible. Practically, I mean, at least to my knowledge of literature, there is not much going on directly observations of isotopes of, let's say, less common isotopes of H2. Maybe there is something, but it's definitely not which is happening like intensively in this field.
There is an answer in the chat on the video. You need very high frequencies and very warm gas.
Yeah.
For that. Yeah, because it is asymmetric, but yeah, the energies are still too high.
Yeah, probably frequency too high. So yeah, these regimes also not
2.5 terahertz.
Yeah. So
yeah, I have a question in the same way. So when we talk about star formation, do these ratios of isotopes have some significance in identifying star forming regions or something like that? Do they say something?
You mean, for example, a ratio of different isotopes of CO or whatever?
Yeah, something like 12 CO versus 13 CO, something like that.
Yeah. Yeah. So the line ratio is so first of all, line ratio is something which is used a lot in these fields of studies. First of all, because of a very generic reason, but it's important. So the idea is that if you work with line ratios, you are able to compare more directly different clouds, because if you look, for example, at the total emission of a certain line for a certain cloud, and then you compare to another one, you expect to have different values because the size of the cloud has definitely an impact on the total luminosity intensity you get. So line ratio in principle enable you to compare different clouds because you work with quantities which are largely independent from the extrinsic characteristics of the clouds. Then so a ratio of isotopes can be useful in principle because different isotopes, even though similar, trace anyway slightly different parts. So in principle, if you look at the isotope ratio, you can have, for example, some estimation on the optical thickness of the cloud. That's an example. So optical thickness, is the fact that when you have a lot of material at a certain point, you cannot say anymore how much material you have, because the material which is from your point of view at the bottom of the cloud, you cannot see anymore because it's covered by what is in front. So since normally, for example, in the case of CO, 13 CO tends to be quite less optically thick than 12 CO. So it can reflect better not better, but it is more sensitive to the column density of the cloud because we have less 13 CO. So yeah, ratios like that can help, for example, in assessing how the gas is optical thick, and so as a consequence, what is the column density? So how much density you have on your line of sight and so on. So yeah, you work with optical thickness mainly, not only, but that's an application, for instance.
Guys, I think this is unfair because you simulation people have taken all the nice observational questions. And I don't know about Katya, are you closer to observations or simulations?
Yeah, I'm also doing simulations.
Okay.
Yeah.
You're also in their team. Okay. But you might have something to say, but before that, I have a simulation question because I did some simulations before, not of ISM, but still. I wasn't sure, how did you model in the molecular interactions do you have to take them into account? Is it a big factor, or how does it work here?
You mean you mean in general the modeling of the chemical network, so how we work with that?
Yes, van der Waals forces, chemical reactions, etc.
Yeah. So in these specific simulations I showed you, we model the chemistry on the fly, which means that we do it kind of together with the physics. So to clarify, simulations means, so a simulation means that we fix a grid. So let's think it about a cube divided in a lot of cells, and if each cell has certain physical conditions at the very beginning. So at the beginning, we fix some initial conditions in terms of physics, and also we fix a certain initial chemical network. So in principle, here we just say at the very beginning of our simulation, all hydrogen is atomic and all carbon is in C+. So that's what we say at the beginning. Then step by step, basically as long as the physical condition change, also the chemistry changes accordingly. So for example, if in a following time step there is a cell which achieves I don't know, suitable so a low enough temperature and high enough density, our chemical network, which runs the chemical reactions cell by cell, says, okay, in these cells there will be a certain amount of C+, which we have at the beginning, will react with oxygen, and so then here we have a certain amount of CO. So yeah, so we do that on the fly, so step by step. This is a huge advantage. This has an advantage because you can do it accurately. It has also the disadvantage that this is really time consuming in terms of proper time, and also in terms of memory you need. So that can be done for kind of simple networks. So here in these particular simulations, we have only a few elements. So we have, as I said, hydrogen, then carbon, so hydrogen in different form, carbon and oxygen, basically. We also we are doing some other simulation with a slightly more complicated network, where we have also helium, neutral carbon, different species of hydrogen, so of oxygen, so also O plus or whatever, plus some metals, but still we are around 10 to 15 species. If you want to model a really complicated network with several tenths or 100 chemical species, then you have to post-process. So you don't do on the fly and you just focus on a snapshot you are interested in and you calculate the chemical network separately if you want to use a lot of species.
There was a and also something that we have always asked our guests for the past 2 months, and this is a very serious question. How does your simulation taste and smell like? Okay, taste I can understand because like tastes like computer probably, but I don't know how it smells like. Have you ever tried?
Well, I guess I can imagine the very dense part of the cloud. So for example, like here, they might smell, for instance, like, you know what an overcooked egg smells like?
Yes.
Okay. That could be the smell of this side. Not by joke, but the smell you feel from an overcooked egg is because of sulfur. And we expect, we know that we have also some sulfur in the densest part. So here we expect to hear something like overcooked egg. On the other parts, I would say, unfortunately, they wouldn't smell, and that's unfortunate because actually this carbon monoxide, CO, which we have, is the same gas that every winter causes problems, because when you leave maybe some wood burning in a not enough oxygen room, it produces CO, which is toxic, and you can feel it because it doesn't smell. So that's unfortunate that actually this gas doesn't smell indeed.
Okay. Nice. This is very interesting because lots of people think that maybe space smells like raspberries or something, but it actually smells like. Last time our guest Brand Gatches said that it probably smells like garbage up there. So
now we have eggs.
Very interested. Like this is. I didn't know your computer had so many capabilities that it smells so good. I mean, it's so,
yeah. We have a powerful computer, so.
Yeah, I thought it tasted like it tastes like bitter because you are always debugging. So
that's also true. Especially when you can't find the errors, the bugs you have, then it's very bitter.
Nice. Katya?
Yeah.
Do you have a taste or smell question or something else?
No questions. I actually have quite general question. So
yes, please go ahead.
Yeah, so it's always nice when people show simulations and also synthetic observations. But imagine the situation, like if I'm an observer and I would say like, okay, I want to observe CO and I have an appropriate, I don't know, instrument for it. So I want to observe exactly this star formation region. So can you predict for me what CO would look like and how real actually would be your synthetic observations?
So I think I missed a part of the question, so because of internet stuff. So say again, so I suppose I am a real observer?
Yes. So, and you want to actually observe the CO. Yeah, so you came to the person who are doing simulations and you're like, okay, so what exactly I would see in this star forming region? I don't know. Is it worth to look at it? I mean, in general, you can model some physics, but can you say like for an exact region, what the person would see, or I don't know, with a 90% of probability, what person can observe?
Well, in principle, I would say yes, because I mean, it depends on how much you know about you know in advance about the area you want to observe. But yeah, I mean, so the idea is that we think at least that the correspondence between the CO and the H2 is kinda tight. Not exactly. We have a sort of uncertainty, which is not nothing, but you know, in physics, if you are within a factor 2, you are kind of happy. So we can reasonably assess how much H2 we have starting from if we have a certain amount of CO. Maybe even better if we use less common isotopes like 13CO or C18 or whatever. Given that, you know, also the correspondence between star formation rate and H2 density is kind of tight. I think there was an example, but there are a lot of in literature. So that this correspondence is thought to be kind of tight. So yeah, I mean, if we know enough things about a certain area, so how many stars are formed, for example, then we can probably within a factor of 2 or so predict reasonably how much CO we will observe. It depends a lot on how much we know about the source we are interested in, basically.
Okay, thanks. And I have just small following question. So what do you think will take longer? Assuming that you already have arranged computing time, so just do the whole simulations for these observations and post-process them and give the pictures to the observer, or just go and observe it if you also already arranged the time for the telescope?
Yeah, that's a good question. I fear like I don't know. Depends a lot on how much detail you want to have. Probably, you know, if you have if you are absolutely sure that then in the time you want to observe, everything is fine. So there is no wind, no storm, no whatever. Two things can be. I mean, you can think about comparing those time scales. The big advantage of simulations is that they don't depend on the weather. So you are sure that you're not going to go to the telescope and then you have 1 week in a row of rain and storm. And so it's basically less likely that you can waste your observation time.
Yeah, thanks. Think about the arguments.
Yeah, I mean,
simulations
that's something you cannot neglect. So
yeah, you should just, you know, convince people that better to use simulations than observe.
But that's a nice argument, isn't it? So
yeah, sure. Yeah, okay, thanks again.
Welcome.
Would it be okay if we keep this video up, since you will be writing proposals in the future and you will have to sort of tell them how good your simulations could be? And I think you gave a really good answer, so I guess it'll be fine.
Yeah, sure.
Yeah. Craig, do we have any further questions in the live chat session?
Nothing in the chat, no.
Yeah, okay, then we can move on to the Astro News session. And thank you so much for Stefano. Thank you so much. It was very good.
You're welcome.
And if you like, you can stay on and
sure.
watch it.
Oh yes, please stay.
Yeah, sure.
Yeah, please. Yes.
Join in the discussion.
Yes.
So
Parit, now we can.
Yeah, thank you, Alina. I will share my screen. I hope you see it as I want you to see it. Okay. I guess it's fine?
Yeah.
Okay.
That's good.
As always, after this serious nerd chatter, let's bring you some exciting astro news from the past month. All right, so the first news feeds right into what discussion we just had. Essentially, it's also about feedback. So, haha. This is helping nebula feel younger. So there was a study that was recently published, which was about the effects of stellar feedback on RCW 120, which is a very spectacular nebula. And it was studied by an international team, including University of Cologne astronomers, Nicola Schneider and Robert Simon, and lots of other colleagues of ours. So what they found is that stellar winds cause the region around this star-forming region to expand rapidly, which enables them to constrain the age of the region. Now, essentially now, after the study, less than 150 years old, which is very young for such a nebula. And these observations were taken using the upgrade receiver on the Sophia telescope, the flying observatory, only one of its kind in the world. You can see here at the center of this ring in the picture, there are a couple of giant stars, and the intense ultraviolet radiation has carved out this bubble, and they blend in with the other stars with, when viewed at infrared. But yeah, this green ring you see here is hit by winds and intense light from the massive stars. And the green color represents infrared light coming from tiny dust grains of polycyclic aromatic hydrocarbons. Inside this bubble, these small grains have been destroyed, the bubble you see inside the green ring. And the red color shows about a bit larger, hotter dust grains, which are heated by the massive stars. I guess this is what also Craig is working on, and since this is supposed to be a PDR region, right?
Yeah. I could. Slava's working on this, like with the observation side, but yeah, this is definitely something that I would be interested in modeling.
Yeah, and there are pretty cool feedback mechanisms that happen inside these nebula. For example, also Stefano might be working with something like that, because stars don't just stay there. They move around after they are formed. Sometimes they go to another place. Sometimes they're big enough that they can create their own clouds from their own from the matter that they were formed inside the matter from which they were formed, and they can push the matter away and form these kind of clouds that we see. These are very spectacular. So yes, there's one main star in the middle, and this star basically causes this cloud to make new stars, and then becomes a star forming region. Right. So then we move on to the next big news. Yes, this is big news. Unicorn black holes exist now. Yes. Somebody had to take unicorns to space because there was a recent publication by Ohio State astronomers in the US, which details discovery of the closest and smallest black hole ever found. There are, of course, many candidates, but this is a promising one. And the other candidates are also not confirmed yet for the smallest black hole found. Now we are talking about stellar black holes, not like black holes that form inside the CERN super collider, which they do, I guess. But yeah, this is serious, because the red giant that the black hole was found around is only 1,500 light years away in the Monoceros constellation. Monoceros is another, I guess, heftier sounding name for unicorn. Monoceros just means unicorn. That is also why people are excited that this unicorn black hole was found in the unicorn constellation. So it's a physical unicorn and historical unicorn. So okay, it's justified. So the physical reason it's called a unicorn is because this black hole is a contender within the stellar black hole mass gap. which means usually black holes are not found in the mass gap, which means from 3 times the solar mass to 5 times solar mass is the mass gap between which not many black holes have been found. Also because also not in simulations sometimes. The problem with simulations is that we don't know much about supernovae and how supernovae collapse, and in what one fraction of a second is it decided that the star that is exploding will become a neutron star or a black hole is not understood yet. Neutron stars are what lies below this, because if a supernova is not that, actually, if a supernova happens, usually a neutron star is formed, and a neutron star, the heaviest neutron star observed yet, is supposed to be around 2.5 times the solar mass. And above that, we do expect black holes, but we don't observe too many. So yes, this is a big discovery if it's confirmed in the coming months. But I still ask, like, unicorn, seriously, I don't get the fantasy, or like I mean, we do have rhinos, right? So rhinos are basically unicorns. So what is the mystery about?
I don't know.
Anyway, what do you guys think about this?
Was it released on April 1st? Because it sounds like a joke.
Close, actually, April 21st.
Okay.
Yeah. Okay. Then we move on to, if you guys don't have comments about unicorns, then we move on to something better.
No, we all are in a serious mood, so we don't have a comment on unicorn.
Because you're serious about unicorns?
No, we are serious about like astronomy and learning. So yeah.
Okay, that's better to know. Thank you. All right, the tweet of the month. I mean, look at its little legs. This is from a very serious scientist who was swooning and spreading love about this helicopter that you see here. Yes, it's a helicopter, not a drone, but the special Ingenuity helicopter, which is the Mars helicopter. The first helicopter on Mars, the first flying object on Mars, essentially to fly last month. This is very recent, and it is a big achievement of humanity. A little background is that NASA conducted its first flight on Mars around, I think, April 19, and which was supposed to be like a short hop, for this helicopter called Ingenuity. But this demonstrated technology that would prove critical to the future of human space exploration. It only flew the first flight about 10 feet above the surface of Mars for about 40 seconds, but it's big deal, and I'll tell you why. Flying close to the surface of Mars is basically like flying at around 87,000 feet on Earth, which is 3 times the height of the tallest mountain in the world, which is Mount Everest. It's very hard to fly there, no doubt. And the record for how high a helicopter has ever flown on Earth is 41,000 feet, so about half of that. I don't know also why all my figures are in feet, but let's go with that. The rotation speed of this helicopter, of the blades of this helicopter, is about 2,500 rotations per minute, which is not just sounds a lot. This is actually a lot, and this is actually 5 times what you have on Earth. So a helicopter on Earth would have just about 500 rotations per minute. It is very hard to create something that flies at such low air densities and also at such high speeds for its blade. Very interesting implications for this technology. Not not only that you can basically fly such an object at really tall heights, for example, on top of Mount Everest, where it is not yet possible. This kind of technology will also be helpful for missions to Saturn, for example. So there's a Dragonfly mission. I don't know if you've heard about it. It's going to Saturn's moon Titan in 2027. I hope it is. That's what NASA says, at least. And the arrival will be 8 years later, but then it will be the first helicopter to fly in the outer solar system. This is the moment that we will look back as the first time it happened outside of Earth anyway. So yeah, exciting stuff.
Did you say 80 years later?
8 years later.
8 years. Okay. I heard it 8 years later. Okay, sorry.
80 years later, we go to the black hole that we just talked about.
The unicorn.
The unicorn.
But also, sorry.
Yeah.
No, I was thinking that also, I mean, it's also kind of amazing because, I mean, they definitely have to automatize a lot for this helicopter because, you know, a signal from here to Mars take 10 minutes to arrive and 10 minutes back. So it's not really that you have a joystick and you rule it. So it has to do a lot of things on its own. So that's also amazing.
Yes, it was basically just a programmed toy on Mars, right? And
yeah,
before the first flight, 1 week before the first flight, they had a software glitch. Since they cannot control it with the joystick, they had a software glitch, which means it's serious. Thankfully, they solved it, and then they had the Wright brothers moment. But yeah, it is scary to fly such things away so far away from you.
Yeah.
Yeah. This slide was supposed to. Okay, this is just the official handle of NASA's Percy rover, and they obviously shot videos of the helicopter, which for some reason is not visible here. Let me see if it works. No, it does. Do you see it?
Yeah.
Oh, cool. Okay. Okay, then enjoy the show. You can see on the right, near the right corner of the screen, you have this little flying object going up. People were even so excited about this that they were so psyched. Oh, look, there was the first time a robot took a picture of another robot. Huh? I love how space people splurge their love on what they create. Absolutely. Okay. This is important also for 80 years in the future, as Alina pointed out. A lot of us here at University of Cologne are part of this collective called Astronomers for Planet Earth. And on Earth Day this time, last month or in March? Okay, I don't remember Earth Day. Thank you.
I think April, somehow in April, but
April 22nd.
All right. Every day is Earth Day, guys. What are you talking about?
Yeah.
Okay. Anyway, Earth Day 2021 happened, and Astronomers for Planet Earth released an open letter that urged all of astronomy departments, science departments, and generally people who are in the business of creating knowledge to sign this open letter. Okay, they urged only astronomers and connected people to sign the open letter, but it was meant for institutions and societies that deal with the creation of knowledge. And it is urged that we should all force our institutions to adopt sustainable models for how we run our buildings and how we operate at universities, etc. And I also urge you, if you are connected with astronomy in any way, amateur astronomer, past astronomer, current astronomer, unicorn, please please sign this open letter. Go to astronomersforplanet.earth and support this cause. Thank you. Back to Craig and Alina.
Yeah, thank you, Berit. It was really nice. Yes.
Thank you.
So that's it for today, I guess, and we still have some comments from Uliana about your discussion about the telescope and observation and simulations. So she was telling CO is observed with ALMA in millimeter and sub-millimeter. So it's not dependent on the optical quality of the atmosphere. So you can still observe it. So people are still writing and watching our videos. So we'll get back to those comments later. And if you don't have any questions, then we can stop it today. So whoever is watching, stay safe and subscribe, press the bell notification, follow us on Instagram and Facebook. So see you in our next event.
Yes. Also, like, answer the questions. We have weekly quizzes on Instagram.
Yes.
If you answer all the questions correctly, then you could be one of the people that's meeting with us live during the event, like Ekaterina.
Yes.
Good to
So
have
thank
you.
you.
Thank you.
Thank you, Ekaterina, for joining us today. So
Thank you very
and
much.
thank you, Stefano, also.
Bye-bye. Yeah.
Thank you for the talk.
Okay. Bye-bye, everybody.
Bye.
Bye-bye.
The stream has ended. Yeah, I have to